All right, so there's a couple different ways we can approach this problem. And none of them are particularly straightforward, but they're not terrible. So we've got a carousel, and one of the horses is here, and the other horse is here. And this one is 2 meters away, and this one is 4 meters away. And the whole thing is spinning so that it makes 1 revolution every 5 seconds. Now, there's a couple ways to approach this problem in that we've been focused on one kind of velocity so far, and that's been the linear velocity of an object traveling in a circular path. So we've talked about the fact that this horse has some, I use the word tangential velocity. And I introduced the idea that the carousel as a whole has what's called a rotational velocity. And I even gave it a symbol, the Greek letter omega. But I didn't talk about that particularly much. I did say in class something you could probably reasonably come up with is that the tangential velocity would be how long it takes to make it around one circumference. That you could use that as a way of calculating what the linear velocity is. There are other ways to do this. This is just one way to do it. And I'm going to show you 2 ways to do this problem. So I'm going to show you the first way for the kid that's 2 meters away. And we'll calculate the net force on them. Now, it just says, with how much force does each sister have to hold on to their horses? So that suggests to me that the sisters probably are experiencing a normal force from the horse, and then the weight that they are experiencing downwards, but they're having to hold on with some force to the left. Would you guys agree with that? So that's a combination of their legs around the horse and their hands around the bar that the horse is connected to, or whatever. So I'm expecting that it's that unbalanced force that they're interested in. So net force equals MAC because they're traveling in a circle. We have to deal with the force that is towards the center of the circle, and I think this one is. So I'm just going to write that this is the force experienced for them to hold on, the hold on force. And that equals their mass times V squared over R. That all okay? All right. Well, I need V. I think I can get it from what's written here. It seems to me that their tangential velocity is going to be 2 pi times the radius. I need to put this in meters, so that's 2, divided by the time. This needs to be in seconds, and it already is 5. So 4/5 pi. You'll have to work that out. You know what pi is. You can figure out a velocity and then take that over here. So I'll have 30 times 4/5 pi squared divided by 2. And that should be how much force it takes for them to hold on. Any question about that? Yep.
If we're solving for pi, should we just use 3.14?
That's pi. So yeah. Don't leave it in terms of pi. Get a numerical answer. So I want to show you a different way to do this problem that could make future problems easier. All right? And we talked about it, but it does take a little more work on the front end of the problem. Are you ready? And I would take notes on this. Omega is an angular speed. As an angular speed goes, and I'm going to erase the stuff that's here. linear speed equals angular speed times radius. You may not know that to be true, but it's been kind of given to you in another format. Most of you know that circumference equals 2 pi times the radius. You guys know that already? Well, you had geometry. So I'm supposed to be able to count on the idea that arc length equals angular displacement times the radius. Like you learned this way back when you had geometry. Now, I don't know if you remember this from geometry or not. So if you don't, I'm teaching it to you now, so I expect that you'll learn this. Okay? So this relationship only works if the angular displacement is in radians. Now, this is why circumference is 2 pi times the radius. A circumference is the arc length of an entire circle, and the angular displacement to go around an entire circle is 2 pi. So that's why the circumference equation is just this equation for an entire circle. You guys follow along with that? If you don't follow along with that, this would be the moment to say, no, Mr. Shelton, I don't understand what you mean, so that you get it out now when later when I expect you. So I assume, because you guys are not saying much, but out of the corner of my eye, I'm finally seeing some people shift a little bit. Good. What's your question? Okay, which part? Do you know what radians are? Well, that's probably why. A radian is another way of measuring an angle. Do you know that? So then let's just for a moment talk a little bit about radians, because you will need to know this for several things this year. There are multiple ways to measure to measure angles. You guys should be familiar with degrees. Can I assume that most of you are? So if most of you are familiar with degrees, then there are some things that are similar between degrees and radians. But they're just angle measures. One of the things about degrees is an old way of measuring angles that's related to some other geometric things in nature. But basically, 360 degrees is equivalent to 2 pi radians. The problem is that radians aren't actually a unit. And that's hard for students to understand. And I don't want to go into too much of an explanation, but the word radian comes from a different thing, something you were supposed to do back when you were in elementary school, but most of you didn't. How many of you proved pi when you were in elementary school? No? Like, you didn't measure it?
I think I did. Maybe.
You think? It may not have been a memorable moment for you. If it were me and I were going to do it and I taught elementary school, I would have told everybody in my class to bring to school something round one day. Now, most of you probably have something with you right now that is round, a water bottle or something like that is round. If I was to do this in our class, I would just break out all the cups that are in my storage closet, and I'd give everybody a different cup. Now, I bring it up because in elementary school you can do this kind of thing and have a fun activity, and the kids may or may not get anything out of it. But all you have to do is take a piece of string and tie it around the round object. Right. Then take that piece of string, cut it, and measure how long it is, because that would be the circumference. Right? You guys follow where I'm going so far? Well, you could then take a ruler and place it across your circle thing, and that would give you the diameter, right? You guys following along so far? Well, circumference equals 2 pi times the radius. You guys do know this, right? But that also means that it equals pi times 2r, which is pi times the diameter. All good so far? So you give a bunch of little kids some string and a little ruler, and they can measure circumference and they can measure diameter for all the different circles they can find in the classroom. And then you tell them to take their calculator out and divide circumference by diameter. And they'll, of course, get pi. Everybody in the classroom gets 3.14. And you can say, see, we all get the same thing. Pi is a part of nature. It is a relationship between the diameter and the circumference. And then you can go usually one step further, which is to give them another piece of string and put a pin in the piece of paper on one side and a pencil tied to the other. And show them how to make a circle with a piece of string. Good so far? So you make them make a piece of a circle, like a little bit of arc. With their protractor, they can measure what that angle is. And you can help them figure out what that angle is in radians. And you can show them that if they take that value in radians and multiply by the length of the string, they'll get whatever this length is. It's a simple activity you can do with elementary school students. It does require they kind of catch on to the fact that there is a ratio between circumference and radius, and that ratio is 2 pi. It does take that in order for them to kind of catch on. So what I'm trying to explain to all of you in this conversation is that there are 2 pi radians in a circle. That's just the way it is. That's the number of angle measures. It has no units. We equate that with 360 degrees. But it allows us to use the concept of circumference for just pieces of arc. Now, the reason I want to go here and the reason I'm willing to take some time to explain this is if you're traveling on a circle, you're on the edge of the circle. For every moment in time, you travel some amount of arc length, correct? For every moment in time, do you follow what I'm saying? Because you're traveling in a circle. So if I say it takes 5 seconds to go around the whole circle, and I say, well, in 1 second, you have done a portion of a circle, then we could figure out how much circle you've traveled on. We would need to know the angle measure, what 1/5 of a circle is. We know a whole circle is 2 pi, but if you only traveled for 1 second, then you would have traveled 1/5 of that circle. You following that? Okay? Well, we might prefer to find out how fast you're going. What's your linear speed? Because I think the person on the outside edge travels a bigger arc length than the person that's in the middle. Does that make sense too? So one way to do that is to just divide both sides by how long you're traveling. This would make this side a value that's in radians per second, or degrees per second, or rotations per second. And it would make this side something in meters per second, right? Because it's going to be an arc length in meters divided by time in seconds. That's important because that means I could find a relationship between an angular speed and a linear speed. The only problem is the only way I can make this work is if this is in radians. So the only way this works is if we convert this to radians. That goes back to the circumference equals 2 pi times r thing. The whole thing about the circle is based on the idea that we're in radians. Now, I don't want to make this harder than it appears. What I want you to see is that the entire ride is traveling at the same omega, right? Every part of the ride is going around 1 revolution every 5 seconds. Does that matter whether you're on the inside horse or the outside horse? I mean, will the inside horse take 5 seconds to go around? Will the outside horse take 5 seconds to go around? So both of them have the same angular speed. That okay so far? They don't have the same linear speed though. If you're on the outside horse, you're going faster than the inside horse. Can you see why that's true? Okay. So it appears that just changing the radius changes how fast you're going. Now, that alone might not be a big deal. But if you saw what we did just a minute ago, we took one step and figured out how fast one of the horses was going, right? And then in a second step, we found out how much force was required. I want to reduce that. I want to make this more streamlined. One way to do that is to realize that the centripetal acceleration we have is in terms of the linear speed. But through substitution, through a little mathematics, we could write the centripetal acceleration in terms of the angular speed. Again, you don't have to do it this way. I'm showing you an alternative. And some of you will see why it's worth learning in a minute. Now, of course, I have to do a little bit of algebra here, don't I? So I'm going to do a little bit of algebra, meaning I'm going to distribute the square so that both of them are squared. I'm doing that because I see the r in the denominator and an r in the numerator, and I want to see what we can do to make that simpler. And I notice that one of the r's will cancel out. Do you notice that too? So this will give me omega squared times r. Now this was a lot, and we've taken a long way to get to where I wanted to go. But what this does for us, if I get rid of all of these things that are just part of the trip to get here, is it means when I have net force equals MAC, I could write that as net force equals M V squared over R, or I could write this as net force equals M omega squared times R. This problem is supposed to have me compare one daughter with the other. And the only difference between them is they are at different radii. The way I did the problem the first time, I'd have to find the velocity for each girl. The way I'm going to do it this time, I want to find the velocity that is the same for both girls. And that's the one that's omega. That'll make doing the work a little easier. It does mean, though, I have to find it in radians per second. That doesn't scare me away. That might scare you away. So if you understood this way of doing the problem with v equals 2 pi r over t, then maybe don't do what I'm about to do. Just keep it this way. This will work, assuming you're given the problem in these parameters. It won't work second semester. Second semester, you're going to have to come to grips with dealing with omega. But if you don't want to learn a new thing now, then don't do it this way. But for those of you that are okay, well, we just have to take 1 revolution every 5 seconds and convert it into radians per second. I don't know how good you guys are at doing conversions. My experience has been, 50% of you do this well, and 50% of you have no idea what we're about to do. So I don't know which 50% you guys are. So I want to convert this from revolutions per second to radians per second. The good part is I don't have to worry about the seconds. Right? They're already in seconds. I don't have to make a change there. I have to worry about the revolutions. I have to convert that. I am a unit multiplier person. I can't do it any other way. So I'm going to do this using unit multipliers. And I have reasons for this, for stuff we're going to do next semester, that you might want to learn how to use unit multipliers. To use a unit multiplier, I'm going to multiply something by a fraction. And the fraction is going to be your conversion fact. You put a conversion fact here. But you have to put it in there correctly. I'm looking at the fact that I want to convert revolutions to radians. So the first thing I notice that revolutions is in the top of the fraction. Do you guys notice that? So I want to cancel out revolutions. So I need to put it in the bottom of the fraction. What do I want to be left with? What do I want to convert to? Radians. So I put radians in the top of the fraction. Now I need a conversion fact. I need the number of revolutions per radian or the number of radians per revolution. Do you have a conversion fact? Anybody know that? I mean, I just went over what this conversion fact was quite literally 6 minutes ago. Nobody, huh? Go ahead.
2 pi.
It's 2 pi, yeah. The whole circle is 2 pi. So there are 2 pi radians in every one revolution. Thank you. I went through the whole thing with the circle just so we could be able to use that 2 pi right here. That means, of course, that in this problem, it's 2 pi radians for every 5 seconds. That is the radians per second speed. And there's no need to leave it in terms of pi in this class. So I get a 1.23. So 1.26 radians per second. So if I want to know the force from the 30 kilogram girl, I'll need to put 1.26 radians per second there, and then I can just put in 1 radius at a time here. So for the inner kid, 2 meters, and for the outer kid, 4 meters. Or just realize the outer kid is going to be twice as far away, so it's twice as much force. The reason I like to see that is because it was hard to know how the force would compare when we were dealing with the linear speed, because we used the radius 2 different times, once to calculate the velocity and once to calculate the centripetal acceleration. Here, once you calculate the angular speed first, R is just proportional here. Double R and I double the amount of force. I'll draw a picture of it to help us out. You have to bear with me. They changed the iPad app I use substantially, and it's taking me longer to find everything. So there's the string, and there's something on the end of the string, and it's traveling in a circle. Nope, that's not what I want it to look like. It's traveling in a circle. There. So that look good? All So from the top, it looks something like, this. And the ball's just going around in a circle. And from the side, it looks like this. That all good? All right. They tell me that it's a 50-gram ball, so that's 0.05 kilograms. And on a cord that is 0.5 meters long, which I'm going to say is L, and it makes an angle of 30 degrees, which I'm going to say is theta. And question A, draw a free body diagram. So let's start there, because we tried to do this in class, so I was hoping that would help with something like this. I think there's only two forces. There's gravity acting downwards on it. And by the way, this is a perfectly acceptable problem for me for like the test. This was on the AP exam even. This is perfectly fine. Oh, that's the way it makes arrows now, huh? What a pain. So I have to make the arrow like this and turn it separately. I have got to find a replacement for this piece of software. It's just getting worse and worse. So there's the weight. I don't even like the way this thing draws arrows anymore. It's terrible. And there's the tension. How yucky is that? There. So those are the two forces acting on the bob. Any questions about those two? I have to choose a coordinate system that is aligned with the direction of the acceleration. And as I'm sure you wrote in your notes, because I was very adamant about this, the direction of the acceleration has to be towards the center of the circle. So if this is tension, and this is weight, towards the center of the circle is gotta be horizontal. So I'm gonna make my X direction that way. And that means my Y direction's gotta be this way. Any question about those choices? All right, I'm assuming you can make these choices on your own now. This is where theta is, because those are alternate interior angles. And that means I will have a component of force this way, that is T sine theta, and a component of force this way, that is T cosine theta. And when I break this up into the net force in the X direction and the net force in the Y direction, I'm going to say the X direction is MAC, and I'm going to say the Y direction is 0, because the ball's not accelerating up or down, it's accelerating towards the center of the circle. There's only one force towards the center of the circle, and that is the tension in the X direction. There are several forces in the Y direction. There's the upward force of tension and the weight, and they equal 0. So I've drawn a free body diagram. I've broken it up into my X and Y direction, all the things I was asked to do. Since the net force in the Y direction is 0, find the size of the tension in the string. All right, looks like I can do that. Looks to me like the tension times the cosine of the angle equals mg. So I can just write this as tension equals mg over cosine theta. And you could plug numbers in. You have numbers, right? So you could do that. You have the mass is 0.05. You have the g is 10. You have the angle's 30. I'm not going to do that. I'm going to leave it like this. okay? I'm purposely going to leave it like this. And I'm going to continue the problem with symbols. Are you guys okay with that? But you could stop and put numbers in. In fact, it's not that big a deal. It's 0.5 divided by cosine of 30 degrees. So I get 0.577 for the tension. Is that what you guys get? Plug the numbers in. So you could get a number here. It's not a big deal. I just don't want to because, look, I know more. And I know they could ask the question in terms of symbols instead. So I put the symbols in last. So now using my tension, find the size of the component of tension in the x direction. They're telling me to find this, which is meaning just substituting this in for t. So I'm just going to do that. That'll be mg over cosine theta times sine theta. I'm doing this because this gives me mg tangent theta. Do you guys see that? Sine over cosine. So when I see stuff like that, it's always nice to know that there's maybe a simpler way I could have gotten to the end of this problem without finding the tension. So that's, it's plausible they could do stuff like that. In fact, I'm going to point out something. If I skip this one and just set this equal to MAC, is it clear to you that the M would cancel out if I'm interested in finding something about the rotation of the object? So it doesn't really matter what I hang on this end of the string. It would behave the same way as long as the string doesn't break. I'm doing that because I know where this problem is going to go. It's going to ask us to figure out how fast the ball is traveling. And I know that that's got to be related to v squared over r. And that's eventually where it's going to go. Or omega squared over times r, one of the two. But they want me to find the velocity of the ball. So I'm going to do that. So here we go. I'll need r. I'll go back to my picture here. R is the radius from here to here. It is not the length of the string. You guys need to be aware of that. You'll make that mistake. You do it all the time. But it is not the length of the string. I mean, I see that it's probably related to the length of the string because I also see that there's some triangle in all of this. Do you see a triangle in all that? So I think the length of the string is related to r. Based on what I've just drawn there, it's related by the sine because it's the opposite side. So if I want to find r, it's L sine theta. And now I'm just going to go ahead and start putting numbers in because we're at the end of this problem. So over here I've got G, which is 10 tan 30 equals v squared over r. Well, r is the length of the string, 0.5, times the sine of 30. And that's got to be 0.5 times 0.5, or 0.25. So that makes this 0.25. Well, now I gotta figure out what v is. So 10 times the tangent of 30 times 0.25. And I get that v squared equals 1.44. Is that what you guys get? Hope so. G was in meters per second squared, and we multiplied by meters, so that's in meters squared per second squared. And I'm going to take my 1.44 and take the square root and find the velocity is 1.2 meters per second. That's fine. No worries. I want the period of oscillation now. The time it takes the ball to make one revolution. I don't know if you've been paying attention or not. If you've been paying attention, you know that I gave you a way to do that. If you haven't been paying attention, I'm going to show you that I gave you a way to do that. The velocity has to equal one circumference divided by the time it takes to go around the circle. So if I want to find out what the time is, I can just plug it in here. I know the velocity is 1.2. I know the radius is 0.25. And I can find the time. I don't think all of you can find the time. I think some of you are going to make a stupid algebra mistake here because you have trouble whenever there's something in the denominator. And I've been trying to point it out all semester, but a few of you will make a mistake. This is going to be 2 pi times 0.25 divided by 1.2. Two times 3.14159 times 0.25 equals divided by 1.2, and it looks like it takes 1.3 seconds. Ta-da. Is that what you guys get? 1.3 seconds? Yay, go team. One of the things about this problem that I think is best served is if you do this problem in terms of the angular speed of the record and not do it in terms of the linear speed of the bug. And for some of you, I don't know if you know what that means. We talked a little bit about it, but I don't know how deep into it we got. But the bug is sitting somewhere on the record. And the record is spinning at 45 RPM. This is an angular speed and not a linear speed. We talked a little bit about angular speeds versus linear speeds when we first introduced this topic. And I didn't go into it in too much depth, but the whole idea about the angular speed is that everything on the record has the same angular speed. So whether the bug is there or the bug is here, the bug would have the same linear speed. There's advantages and disadvantages to staying in terms of the angular speed. The biggest advantage is that you don't have to do conversions to linear speed every time the bug moves from one place to another. The angular speed of the bug will stay the same the whole time. The disadvantage about using angular speed is that it has to be in radians per second, and you guys have difficulty doing conversions. So I can do this problem either way, but I think we're best served by doing this problem in terms of angular speed. But you guys asked about it, so what would you like to do? Okay. It will require a couple of small changes. So let's talk a little bit about those changes first. I'm going to put something on the board that I put on the board last week, and it was a discussion about tangential speed. This is me putting a T there to remind us that we're dealing with an object traveling in a circle, so at any moment it has a linear speed that is tangent to its motion. So I put a T there for that purpose. This way, if the bug starts walking towards the center, we would have radial speed and tangential speed. They would be different. This equals the angular speed times the radius, but only if the angular speed is in radians per second. Now, when I was talking about this in second period, I had a lot of concerned students. One of the concerns was that people didn't understand what a radian was, and from there, other concerns sprouted up. So how many of you are unclear as to what a radian is? Okay, that's fine. The simplest way to say it is that a radian is just an angle measure, like a degree. It's more complicated than that because of actually what radians are. But the simple way of saying is that it's just another way of talking about angle measures. So where we know an entire circle is 360 degrees, that would be equivalent to 2 pi radians. In fact, that would be your conversion fact. Obviously, this conversion fact could also be written as pi is equal to 180 degrees by just dividing by 2. But it comes from the fact that if you go around the entire circle, you have gone around 360 degrees. Now, the 2 pi, mind you, comes from something else. And I have found that most of you never measured pi when you were in like elementary school. Is that true? Did you guys measure pi, like do a simple activity to measure it? So you guys don't know where pi comes from then. Is that true? That's a disservice. We could do it. I mean, we could do it in here. It's like a third grade activity. So it's very simple. The problem is that I don't think you'll be fascinated by it. A third grader might be. All you have to do is get something round. And so you tell every third grader to bring in a cup or a can or something like that. You want to have, the idea is to have different things that are round but different sized. So that would be the goal. You guys probably have something around near you that we could do this with right now. But you get your thing out there that is round. And you give every kid some string. And you tell the kids to wrap the string around your item that's round. Then, once you've done that, cut the string and lay the string out in a line. And measure it. This is the circumference. Then you tell them to take their little rulers in their wee little third grade hands and put it across the top of their thing and measure what the diameter is. So they get the diameter and they get the circumference. What people don't realize is pi is a ratio. Pi is the circumference to the diameter. That's what it is. That's where it comes from. In nature, the Greeks figured out that every circle, no matter what, this ratio was the same. And so you have all the kids do it in the classroom. They type it into their wee little calculators, and all of them get the same number. And they're like, see, it's the same for every circle in the universe. Pi is a fundamental part of nature. And they don't understand the word fundamental, and they don't get what nature is and all that. But you're trying to show them that this is kind of part of the fabric of nature. It wouldn't matter what the numbers were that you chose. It wouldn't matter what the units were, because if this were in meters, this would also be in meters. It would cancel out. So pi is a unitless quantity. And then you can go one step further if you're really trying to get the kids to understand and say that, well, we often measure things in terms of the radius. So if you divide, if you realize that the diameter is 2 times the radius, then the circumference divided by the radius is 2 pi. You following me so far? Now that's where pi comes from, but it also shows you that there's 2 pi of them in one circle. So you take the same string and you put a pencil on the other side of the string. And you can teach them that you can make circles with this, where the string is going to be your radius. And you ask some questions about, well, if you have to go all the way around in the circle, how big will that circle have to be? And they should be able to see from here that the circumference would be 2 pi times the length of that string. You can teach them things like this about circles. And you were taught in geometry that an arc length, they use a S usually for arc length in most geometry classes, is equal to a part of a circle times the radius. You learned that in geometry in the 8th grade. You learned about segments and sectors and portions of circles and arc lengths and stuff like that. It was just something that came up in the 8th grade. And nobody probably ever connected the fact that if you use this, okay. If you use this is also saying that circumference is equal to going around the whole circle times the radius. That's all that is. So this is where radians have come from. Radians are actually part of nature. Radians are supposed to be a unitless quantity because the meters canceled out here when you measured pi the first time. It's just another way of measuring an angle. It's all it is. But it has unique features in that it's built into the fabric of how circles work. And so it has some special qualities. Now, here's where we get back to physics. If you know how long it takes to go around a circumference, and you can divide by t on this side, what you would get is your linear speed is equal to your angular speed times your radius, where this would be delta theta over t, that's linear speed, and this would be how far you've moved over t, that's linear speed. So this is where that relationship comes from. But it's important to realize that relationship only works when omega is in radians per second. That's important. So I go back over here to my picture, and the reason why I think using omega is better is because we know this problem is going to have centripetal acceleration in it eventually. And we know that centripetal acceleration is v squared over r. Well, if I do substitution, I will have a different way of dealing with centripetal acceleration. That's based on the angular speed and not the linear speed. It will require that I do some arithmetic on the right side there. I'll have to expand that square, and then I can divide out one of the r's, and I get a different way of dealing with centripetal acceleration, a way that has to deal with angular speed and not linear speed. There's advantages to this. One advantage is that will you notice that the angular speed is proportional to the radius? I'm sorry, the centripetal acceleration is proportional to the radius. That it requires more acceleration as you move towards the edge of the speed, or the edge of the disk, or whatever it is. It's not clear from here that that would be true, because the r is in the denominator. But you're supposed to know that as an object moves towards the edge, their linear speed increases. So I don't know that that's clear. So this makes it very clear that you have to hold on more the further away you are from the center. That's what that's saying. And it's just not clear any other way. Now, that was an explanation as to why dealing with omega is, I think, better in this problem. It's also an explanation as to what radians are and where they come from. The only thing you have to carry with you is a conversion fact, that there are pi radians for every 180 degrees, or there are 2 pi radians for every 1 revolution. Those are conversion facts. We're never going to measure angular speeds in degrees, so this will never come up. We will, however, measure rotational speeds in revolutions, so this one will come up. So in this problem, going back to the problem now, if I'm starting the problem from scratch, none of this was necessary to understand this problem. In this problem, they give me that the bug is traveling at 45 revolutions per minute. Regardless of whether I wanted to do this problem in terms of angular speed or do this problem in terms of linear speed, I would have had to convert this somehow. I would have had to either use this, where I convert the time to something, or I would have had to convert this to radians per second. One or the other, so it's going to be the same amount of work. I'm going to assume, based on about 5 people in this class, that you can't convert this, that you don't have a method for converting from revolutions per minute to radians per second. I've watched you guys do conversions, and not in this class so much, but I know some of you, I've watched some of your work. I think you need a method. So who feels super comfortable doing conversions? Okay, I'm going to give you a method. If you are unfamiliar with this method, write it down. It's not hard. My expectation is that you had a method before you came to this class, that chemistry taught you a method. But having taught chemistry now, I know that that's probably not true. So you should be good at this, no matter what. No matter which class you end up taking in a school for stuff in the future, you might have to do conversions after this. So you start with what you have, and you write out what you want. That's the first step. Start with what you have and write out what you want. I have revolutions per minute. You understand that per is where the division sign goes, right? So anything per something else, the per is telling you what's on top and what's on the bottom. So meters per second, the meters go on top, seconds go on the bottom. That's what the per means in all of those. So if I gave you rotations per second, rotations would go on top, seconds would go on the bottom. Per is the line. All good? All right. We're going to use unit multipliers. So for anything that has to be converted, you need a multiplier. So to me, I see two things that have to be converted. I have to convert revolutions, and I have to convert minutes. Does that make sense? I also know that I'm going from minutes to seconds. I have to know, do I have a single conversion to do that, or will I need multiple conversions? For example, if it was minutes to days, I don't know how many minutes are in a day, do you? I might need two conversions. I might need to do minutes to hours first, and then hours to days second. Does that make sense? So you have to kind of think in advance, well, how many conversions am I going to have to do? But I know one conversion that goes from minutes to seconds, and I know of a conversion that goes from revolutions to radians. So I'm going to need to do two total conversions. So I'm going to put a parenthesis with a line in it for a fraction, and I'm going to do that twice, once for each one of the conversions I'm going to have to do. Okay, unit multipliers. Each one of these is going to is a unit. It's going to be one conversion. Now, I have to pick one of these to start with. So do I want to start with the revolutions or the minutes? Revolutions. So I notice revolutions is in the top. So in my multiplier, I put revolutions in the bottom to cancel it. I want to cancel that one out. And then I put radians in the top because that's what I want to go to. I want to be left with radians. The reason I like using unit multipliers is that you never have to remember if I'm dividing by something or multiplying by something. This handles that. So anytime you do conversions, you can do them this way, and you'll never get it wrong by multiplying when you should have divided. You'll say, I didn't know whether I had to multiply or divide. This takes that away. Now, I do need to put my conversion fact in there. So you need to know your conversion fact. We know from just talking that they're related by 2 pi. It's 2 pi radians for every 1 revolution. So I put the 2 pi here and the 1 there. Put my conversion fact in. I'm going to move on to my next conversion fact. My next conversion fact is the minutes. I noticed the minutes are on the bottom. Do you notice that? So I'm going to put minutes on the top. I want to cancel them. And I also know that I want to be left with seconds, so I want seconds on the bottom. I need a conversion fact. I have a conversion fact. I know that there are 60 seconds for every 1 minute. There. Now I can't screw this up unless I somehow put it in my calculator wrong. I multiply across on the top, and I'll get 45 times 2 pi. Multiply across on the bottom, and I get 60. I need to work that out, but my answer will be radians per second. So this is where, you trust your calculator. I got 4.7 radians per second. Is that what you guys got? Excellent. So we now know the radians per second. Is that particularly hard to do? You've seen it done once now. I don't think it's particularly hard, but I don't know. You guys will have to figure out whether that's hard or not. But because I have that now, I have omega for this problem. So I know that omega is 4.7 radians per second. I'm going to proceed with the problem now. Everything else was about learning about omega. We haven't really touched the problem. Let's get to the problem. A bug is on a record as revolving 45 rotations per minute, which we now know is 4.7 radians per second. The bug is located at a distance 10 centimeters from the center of the record and has a mass of 15 grams. What is the net force required for the bug to stay on the record? I think the bug is experiencing 3 forces. I think there's a normal force, I think there's weight, and I think there's friction. I think those are the forces acting on the bug. Does that sound good to you guys? First problem isn't really asking me about these individual forces. It's asking me about the net force acting on the bug, which we know has to equal MAC. So I am just going to find the net force acting on the bug. I'm just going to leave it like that. That'll be the mass of the bug times, in this case, omega squared times r. I'm going to use that. Now I have to put in all the stuff and punch buttons. That's all that's left. The mass is 15 grams. I better put that in kilograms. I know how to do that, and if you don't, unit multiplier will tell you how to do it. It's one conversion to go from grams to kilograms. Don't screw it up. I need omega, 4.7 squared. I need the radius. That has to be in meters. They gave me 10 centimeters, so that's 0.1 meters. This is the net force required for the bug to stay on the record. And I get 0.033 newtons. We all good? Alrighty. What is the minimum coefficient of static friction that will keep the bug on the record? Alrighty. So minimum coefficient of static friction. I'm just going to look at the picture there, and it looks like net force is in the x direction equals ma, and net force in the y direction equals 0. Seems to me that the normal force minus the weight equals 0, and it is a frictional force that keeps the bug on the record. And we know that this is 0.033 newtons. All okay? Well, it looks to me also like normal force is going to equal mg, which is 0.015 times 10, or 0.15 newtons. Any questions there? I'm not doing anything outside of our set of steps, am I? This is all the stuff our steps would have gotten us to, but the problem asked about the coefficient of friction, I'm probably going to have to use something that brings in the coefficient of friction to figure this out. And we know that the static frictional force is less than or equal to the coefficient of friction times the normal force. So 0.033 must be less than or equal to mu s times 0.15. Well, that means mu s has to be greater than or equal to 0.22. I like to substitute into anything that has an inequality because I think it's better to know whether I need to be greater than something or less than something for my answer. It asks for the minimum coefficient of friction. This tells me that the coefficient of friction has to be greater than or equal to 0.22. So the minimum would be 0.22. That's the smallest that can be. Okay. The actual coefficient of static friction is 0.4 between the little bug's feet and the record. What is the maximum distance away from the edge of the record where the bug can safely walk? All right, here's the best part about having done this in terms of omega. This is a one-step question now. Well, maybe two steps. We don't have to worry about the linear speed. We know that the net force is proportional to omega squared times r. I already know omega squared, it's a constant. It's not going to change. It's 4.7 squared. This should make finding this answer out more straightforward. Now, I don't know if you know how to do this portion of the problem. We're not really starting over. For example, we know that the normal force equals mg. And we know that the frictional force equals MAC. You guys see that? So frictional force is MAC less than or equal to mu S times mg. Do you guys see what I did there? I'm going to notice that it doesn't matter what the mass of the bug was. So this will be true for any bug or anything. AC is omega squared times R. We are interested in R, right? What radius? How far away can the bug walk and stay on there? So I want R, which has to be less than or equal to all those things over there. We have all of those things over there. Now, the reason why I like doing it this way better is as the bug walks away from the center, his linear speed increases. We wouldn't be able to do it like this without omega. This makes it simpler. This has got to be less than or equal to 0.4 times 10 divided by 4.7 squared. So 4 divided by 4.7 squared. And I find that R has to be less than or equal to 18 centimeters. It's 0.18 meters, but 18 centimeters. I like leaving it in terms of the inequality. If you leave it in terms of the inequality, it tells you kind of the direction of your answer. I know I have to be under this value. If I go over this value, the bug, slides off the record. Now, there is this final question. What will be the linear speed of the bug at that distance? Linear speed equals angular speed times radius. It's got to multiply that answer by 4.7. So 4.7 times 0.18 meters. 4.7 is in radians per second, so I do want you to see something really quickly. The 4.7 was radians per second. And we're multiplying by 0.18 meters. It's important to note that if you have something that's in radians per second and you use it in this way, radians are considered unitless. We write radians in there to remind us that it is an angular measure, but it's a unitless value. So if something else is there, you don't write the radians. So when I multiply the 4.7 times this, and I get 0.85, the radians times meters will just leave you with meters. And we already had seconds. So the radians disappear if there's another unit to take their place. Radians is truthfully a unitless quantity. All right, there's a lot in that question, and all of it fine, testable, stuff like that. I had no trouble with any of this. I think it's easier to do this problem in terms of angular speed, though. It really is. All right. I took a long time to do that one on purpose. If you do this one in terms of angular speed, it's a carousel problem. Both horses on the carousel are traveling at the same angular speed. So if you do this in terms of the angular speed, you can just do the problem really fast 2 different times without having to recalculate how fast each girl is going. So if you do it in terms of linear speed, you'll have to calculate how fast each girl is going because we don't know their linear speeds. We know that the entire ride has an angular speed of 1 revolution every 5 seconds. And we're told that the inner girl is 2 meters away and the outer girl is 4 meters away. So your choice is net force equals m v squared over r or m omega squared over r. So you either find each girl's linear velocity separately and then find their net force separately, or you find one angular speed that applies to both girls, and then find the net force for each girl. It's much easier to do it this way. But it means you'll have to convert 1 revolution per second into radians per second. So let's do that. I'm going to make this conversion. How many things do I have to convert when I go from revolutions per second to radians per second? 1. So I'll need 1 unit converter. I'm converting to revolutions, so I'll put that in the denominator. I'll put radians in the numerator. I'll need my conversion fact, that there are 2 pi radians for every 1 revolution. That's it. Multiply across on the top and get 2 pi. Multiply across on the bottom and get 5. So 2 times 3.14 divided by 5, and I get 1.26 radians per second. All good? All right, well, net force equals 30 kilograms for the girl, 1.26 squared for the angular speed, and then 2 meters for the one girl and 4 meters for the other. So, I mean, I think that's pretty easy to do it that way. Otherwise, you have to find the individual velocities. I think that takes longer. That all good? So, it tells me that the frictional force is 60% of the normal force. So I'll remind you, what they're really saying is that the coefficient of kinetic friction is 0.6. All right, 60% of the normal force. They're talking about kinetic friction. So again, we're talking about kinetic friction, that's mu times the normal force. By just saying 60%, they're just saying that the coefficient is 0.6. It says that we are lifting up on the, the box now. We're applying a force at an angle. So I'm gonna have a applied force here. Oh my God, I hate this app now. I hate this app now. Big hate for this app. It won't let me draw an arrow in a particular direction now. So me and this app are gonna have to part ways. There's gonna be another force downwards. That's gonna be the weight. There's gonna be another force upwards. That's gonna be the normal force. And there's gonna be another force backwards. And I believe these are going to be all the forces that are acting on our object. This is at an unknown angle, though. This is our applied force, this is the normal force, this is the weight, and this is friction. And we're hoping that the object travels at a constant speed, so net force is 0. We need a coordinate system, and I think the best one to use is more. So I'm going to use a coordinate system that is aligned with the horizontal, so something like that. I can choose any coordinate system I want because net force is 0, but if I do it this way, 3 of the 4 forces are lined up with this coordinate system. This makes the most sense. I do have to break up the applied force into components, and there'll be applied force in the x direction, that's going to be cosine of theta, and the applied force in the vertical direction, and that will be the sine of theta. Any questions about this? We've kind of done this problems like this already. We doing okay? All right, net force in the x direction equals 0, and net force in the y direction equals 0. So I'll have FA cosine theta minus friction equals 0. And I'll have FA cosine, no, not cosine, sine theta plus normal minus weight equals 0. All right, that's Newton's laws, right? Now we're supposed to try and figure out how to get to an answer. We have lots of unknowns here. That's the problem. We have lots of unknowns. But they're telling me that my applied force is 450, so I have this one. And they told me the mass of the box, so I have this. I don't have the normal force, I don't have the frictional force, and I don't have the angle. So I need to make some substitutions. I need to eliminate things. So that's where you got to kind of come up with some way to eliminate stuff. And I don't know if you've kind of picked up on this, but we generally, if friction is the problem, you'll have one equation that has friction in it, and one equation that has normal force in it. Have you noticed that? Because friction is always perpendicular to the normal force, so they're always in separate equations. And this can bring them together. So whether I substitute into one of these equations or out of one of these equations, doesn't matter. I just got to pick a place and begin. So I'm going to pick this. I'm going to take this and substitute it in there. That will give me a new relationship. That doesn't have friction in it. So now I'm down to two relationships. Two unknowns, theta and normal. But it's two equations and two unknowns. So I think it's probably easiest to substitute for the normal force now. And that's what I'd do next. I would say normal force equals mg minus fa sine theta. I'm just solving this one for normal force so I can plug it into the other one. So fa cosine theta minus mu times mg minus fa sine theta equals 0. Now here's where you're going to run into trouble. Here's where I don't think you can solve this. You have numbers. You can put all the numbers in you want. You have 450 cosine theta minus 0.6 times 1,000 minus 450 sine theta equals 0. And this was a lot of work to get here, but I'm not sure what you would do with this. Multiply by 0.6, say, and I'll get 450 minus 600 plus, let's see, 0.6 times 450, 270. So 270 sine theta equals 0. Oops, I forgot the cosine, sorry. Sorry. What else could you do? You guys know some things, like I can move the 600 to the other side. But I think you're stuck here. I don't think there's anything else you can really do. Because you have a cosine theta and a sine theta. And you can't there's no easy way to solve for that. There are things that can be done. But I think you're at the end of what you can do. That's why I said this is a very hard problem, hard question, probably beyond the abilities of what you could do. Now, do you know how a person like you could probably do this problem? Plug in 30 and see what happens. And then if 30 doesn't work, go up some and try 35. Or you could plot it. You could put it in your calculator and find out where it equals 600. Those are the ways to solve this. So, but I would say that at this point, what you can't do is probably go theta equals. There's no algebra way to do that. So obviously this will never be on a test like this. I could ask you to come up with an equation. I'm okay with you coming up with an equation. That's fine. It would sound like derive but do not solve an equation that could be used to find the angle. But I'm not planning to do that on any test for you guys. Most roller coasters up their G-force experience by making the roller coaster train travel through a very fast turn. If a turn on Montu is designed to have a radius of 5 meters and is designed for you to pull 4 Gs during the turn, meaning 4 times the acceleration of gravity, what tangential linear speed must the cars be traveling to make the turn? Okay. So, a roller coaster track making a turn. They tell me that the turn radius is 5 meters. So the cars are just going to be making this turn around the track. The tangential speed is the speed that is tangent to the turn, or tangent to the path. So the tangential speed is just a linear speed, like that. And we're, I guess, assuming that the cars are going to have the same tangential speed throughout the course of the turn. So we want there to be an acceleration that is equivalent to 4 times g, or 40 meters per second squared. And they want us to tell them the tangential speed required to make that. So I think that's it. V squared over r has to be equal to 40. Now we know what r is, it's 5, so 40 times r, which is 5, has to equal v squared, so v is the root of 200. Pretty sure that's it. So the cars have to travel 14 meters per second around the turn, which is about 30 miles an hour. Montu isn't especially fast. Doesn't have to be. Most roller coasters aren't particularly fast. They don't have to be. So we'll get to that part. Let's set this problem up. Bug on a record. So here's our record. Center of the record. The bug is somewhere here. And the record is spinning at an omega of 45 RPM. At this particular instant, the bug has a tangential velocity in that direction. Now, we talked a little bit about angular velocity, and I'm not sure you guys, have a good grasp of it. This problem can be done in terms of the angular velocity, or it can be done in terms of the linear velocity. I will tell you, it's easier to do this problem in terms of the angular velocity than the linear velocity. And it's probably true that you guys don't know why, but I'll say it this way. The entire record is spinning at one angular velocity. The entire record is. So we know that this problem has a part where the bug's going to go to another place on the record, right? It says if the coefficient is 0.4, where can the bug safely stand and not get flung off the record? So we know we're going to move the bug around the record a little bit. Every single place where the bug is will have a different linear velocity because the circle they're traveling in is different. So he'll be traveling slower on radii that are closer to the center and faster on radii that are farther away from the center. But the whole record has one angular speed, no matter where the bug stands. So it might be easier for us to just do the problem in terms of that single number changing than having to find a new linear velocity each time. Does that make sense? Now, there are parts about that you might not understand. And from talking with folks in second period and third period, I think I could name a few things. For example, the linear velocity of the bug is equal to the angular velocity of the bug times their radius. I said this in class, but I don't know if you guys really understand what this means. Moreover, it was pretty clear in second period that you guys don't know where this comes from, even though this came from something you did in 8th grade or maybe 9th grade. When did you guys have geometry? 8th or 9th? Maybe 7th for some of you? I don't know. I don't know when they do it anymore. But this was in geometry. You did things like arc length. You guys remember arc length in geometry? And segments and sectors and stuff about circles? Now, look, you can be honest with me and say, I don't remember any of that stuff. Otherwise, I will just count on you knowing it. So if you don't think you remember this, I can step you through it. And I can explain to you things about radians and stuff so that you have an understanding, or at least my expected understanding. But it's up to you guys. It's whatever amount of time you want to spend on this. I'm fine either way. Okay? So I don't think I need to go back to the 3rd grade, but did anybody in here do an activity like in the 3rd grade where you figured out what pi equaled? No? So nobody had that experience? It wasn't like a thing where the teacher said, bring something round to school on Friday, we're gonna do an experiment? All right. It's too bad because, no. It's good for 3rd graders to do it. It's becomes a little bit silly to have high schoolers do it. The idea is you'd grab like your water bottle or a can or something that's round. And the teacher would hand out some string and you would tie a string around the thing that is round. And then once you've done that, you'd cut the string, lay the string out, and measure the length of the string. This would be the circumference. And then she'd hand everybody a little ruler because you weren't required to bring them to school back then. And you'd lay the little ruler across the cup and you'd find out when it's the biggest, because that's the diameter, you'd find out the size of the diameter. And then your teacher, assuming, nice person and all, would say, okay, take out your little calculators and take the circumference and divide by the diameter. And this equals, of course, pi. Now, what's interesting about this, and the reason that it's kind of important, is she would also then usually say, all right, we're going to try something. I want you to measure the diameter and divide it in half. That's called what? Radius. Excellent. Good job, 3rd graders. So I want you to measure out that piece of string to be the same size as a radius. And we're gonna put a pin on one side of it to hold it in place. And then you're gonna put your pencil on the other side. We're gonna tape it on. And then I want you to move your pencil in a complete circle. And I'm pretty sure you guys know what would happen. You'd move it in a complete circle and it would create, obviously, a circle. Because that's how you make circles, by keeping the radius fixed. And then she'd say, look, your circumference was equal to pi times 2 times the radius. And you say, yeah, that makes sense. And then you'd probably take your little round thing, whatever it was, and you'd put it inside the thing you drew, and you say, see how it fits? You drew the same thing as your cup, whatever. And then she'd be all done, and she'd be happy because it would be PE time, and you guys would all leave. And she could have a break finally, maybe go to lunch, who knows. I don't know how elementary school works. But the idea was to show that pi is related to the circumference and the diameter. You guys know more now. You know that 2 pi represents the number of radians necessary to go around the circle. Right? That was what the teacher was trying to teach you with this part. that you'd go around the circle, and that would be equal to 2 pi radians. But she didn't use the word radians, and she didn't talk about it that way. She just said that, your circumference equals 2 pi times the radius. And then you advanced a bunch of years, and you went to your high school geometry class where they said the arc length equals some angle times the radius. But they said that this arc length had to be in radians. Well, they said that because the circumference and the diameter are related. That's where it came from. So if you didn't want to make an entire circle and you wanted to make only a portion of a circle, you would sweep out the number of radians that you wanted to sweep out. And that's how you would work it out. Now, I know that you guys are like, where are you going with this, Mr. Shelton? Well, look, what I want you to notice is that if you're on the pencil and you start going around in a circle multiple times, how many angles per second you cover would be related to how many meters per second you would cover. Do you see that? And that's where velocity equals angular speed times radius. That's where it comes from. It comes right from your circumference formula. However, this has to be in radians for this to work. And why? Because of this. It has to be in radians because of that. That's why you can't use degrees. When you divide your circumference by diameter, you get a number, and we've decided to call that radians. And you probably know somewhere in your past that 2 pi radians is equal to 360 degrees. You probably have heard that before and wondered what the heck a radian is. Well, a radian is just a different way of measuring angles. But the important thing to know about radians is that they're related directly to what you get when you measure stuff about a circle. Degrees was made up from something else. It had to do kind of with a circle, but it mostly had to do with the way circles were spinning, like the earth moving and stuff like that. They just wanted to break it up into some convenient numbers, and that's where that kind of came from. But the idea of 2 pi radians was related directly to stuff you get from a circle. That's why we use it. Now, all of that is to say, when we come back to my class, well, centripetal acceleration is v squared over r. But if I do some substitution, I can write this as omega times r squared over r. And if I take that 2 and put it inside, I'll get omega squared r squared divided by r. And do you notice how one of the r's cancels out? So I'll get that the centripetal acceleration is equal to omega squared times r. What's important here, what you're not getting, and some of you won't get, is that this is telling you that if you have a platter that's spinning, well, how much acceleration you require is just proportional to how far away you stand. The reason why that's different than what we said over here is because what we're saying right here says the amount of acceleration required depends on how fast you're going when you're standing someplace divided by where you're standing. You still have to figure out how fast you're going when you stand there. So for things that are spinning, this is usually better to use because the whole thing is spinning at the same speed. That's why. Look, I know that if this were 10 centimeters, and this one were 20 centimeters, and this one were 30 centimeters, well, look, they're each going to be proportional. The second one is going to be twice as more acceleration as the first one, and the last one's going to be 3 times the acceleration, because they're just proportional to their radius. So use them both. But I'll tell you that when something is spinning and some guy's standing on it, use that one. So the carousel with the horsies on it, use that. Both horsies have the same angular speed. And if they give you an angular speed, use that. Probably going to be easier. If it's a car and a roller coaster, use that one. You're probably going to know the velocity, right? It's not a whole thing that's spinning. It's just cars going through a circular track. So you pick the one that works best for the situation. So because this is 7th period, and because you guys tend to ask questions, which I appreciate. Use this for objects in circular paths. Use this for objects on a platform that's rotating. It will be easier, I promise. It will be the same amount of work most of the time, but usually you'll be able to get to your answers or to an expression faster if you use the right one of those. This problem told me that the record is spinning at 45 RPM, and it told me where the bug is standing. It seems to me like for this problem, angular speed would be the way to go. So let's go back to the problem. The bug is located a distance 10 centimeters from the center of the record and has a mass of 15 grams. What net force is required for the bug to stay on the record? All right, net force. Radius, 10 centimeters. Let's see. I don't need to do this to answer this question, but are there not 3 forces acting on the bug? Weight downwards, normal force upwards, and then probably friction towards the center. Yeah,
The 10 centimeters, do you have to convert that into meters?
We will.
What our speed is?
we'll have to convert everything into meters and kilograms and such. But yeah, we will. So it just asked what the net force is on the bug. Well, net force is equal to MAC. So I didn't need to break this up into individual forces to do that. Net force is just equal to MAC. So the mass of the bug, 0.015 AC omega squared, radius 0.1. See what I'm doing there? Now here's one problem. You would have had to do this anyways, but this only works if we're in radians per second. But they gave us 45 RPM. Is that radians per second? No. What's RPM?
Per minute.
Rotations per minute. How many of you know how to convert 45 rotations per minute to radians per second? All right, I will have this expectation. So if you don't know how, I guess you need to learn something else today. This is something that should have been taught to you. I had a reasonable expectation that you would know this. So, because conversions are supposed to be things you guys can do. I will show you how to do it. I will give you a foolproof method. And I mean that. Even a fool can't break this method. Okay? If you know how to do it, great. Do it your way. But this is the way I would teach you. And since I'm teaching it to you, I use unit multipliers. First, I have to say this, and I don't mean this to be cruel. Per means divide. So it's RPM, rotations per minute. Rotations go on the top, minutes go on the bottom. It means divide. Meters per second. Meters on the top, seconds on the bottom. It is 45 RPM. That is 45 revolutions or rotations per minute. Start by writing your value as a fraction. Next, write out your target. Give yourself some room, but write your target. My target is radians per second. So I'm starting with revolutions per minute, and I want to end with radians per second. That's my target. Do you understand what I mean by target? We're trying to get there. Now, I leave in the middle openings because we're going to use unit multipliers. And this is why I get so mad when a kid says, oh, I don't know whether I'm supposed to multiply or divide by 100 or 1,000 or whatever. If you do this, you'll never get it wrong. I promise, okay? So I want to take the revolutions and convert to radians, and I want to take the minutes and convert to seconds. This is where you have to do a little bit of pre-planning. you need to think in your head how many ways or how many things will I have to do to convert from one of these to the other. For example, revolutions to radians. Do you know a conversion fact that can go right from revolutions to radians? And we just talked about it, so I'd hoped you did, right? Going around once is how many radians? 2 pi, yeah. Yeah, I wasn't trying to make it hard. We did all that over here, right? The whole conversation about going around once is 2 pi. So, yeah, I do think, yeah, I can expect that. And do you know how to go from minutes to seconds? Yeah, can you do it in one step? Like, do you have one conversion fact that goes from minutes to seconds? So I bring this up because what if it was minutes to days? Do you know a conversion fact that goes from minutes to days? Right, you would probably have to go through hours first. You can convert minutes to hours and hours to days. So I'm saying that because I'm trying to decide how many multipliers will I use. I'm going to use one multiplier that will do revolutions to radians, and I think I can do one multiplier that goes minutes to seconds. But if I was going minutes to days, I might need 2 multipliers. One to go minutes to hours, and one to go hours to days. Does that make sense? Well, I hope so. Not everybody's saying yes, but I hope so. But I think I can just do these 2 multipliers. Now, when I say multipliers, each one of these is going to be a fraction. Okay? Each one's going to be a fraction. Let's start with revolutions. Now, you'll notice revolutions is in the top, right? So I want to make sure I cancel out revolutions, so I don't want revolutions in my answer. So to cancel out something that's on the top of the fraction, I put revolutions in the bottom of the fraction. And what do I want to be left with? What am I converting to? Radians. So I put radians in the top. Now I need my conversion fact. What's my conversion fact? 2 pi radians for every how many revolutions? 1. That's my conversion fact. All right, that one's done. Let's go to the next one. Yeah, it's just like stoichiometry. It is just like stoichiometry. That's what I meant. You learned this in chemistry. So you did this in stoichiometry. All right, the next one, I want to go from minutes to seconds. So notice minutes is on the denominator, right? So I'm going to put minutes in the numerator here so that they cancel out. And then by extension, I have to put seconds in the denominator. What's my conversion fact? 1 minute, 60 seconds. There you go. So now you just multiply across on the top, multiply across on the bottom, and what you get is your conversion. I get 4.7 radians per second. Conversion. It's not so hard. We all feel like we can do it now? I hope so. I hope so. All right, so now, again, let's get back to this problem. Net force equals 0.015 times 4.7 squared times 0.1. That is the net force acting on the bug. You will need to tell me what the net force is acting on the bug. No one has an answer? You can do it. I believe in you. Nobody? Look, bell's going to ring 5 times you guys get done.
0.0331.
Thank you. 0.033 newtons. All right, let's go on to the next part of the problem. What is the minimum coefficient of static friction that will keep the bug on the record? All right, now we're going to have to do some physics stuff. We found the net force, but now we're going to do the set of steps here. So when I look at that picture, can I skip to the fact that net force in the x direction is what equals 0.33 n? Is that okay? Or 0.33 n, sorry, 0.33 n. and that the only force that acts in this direction is friction. Is that good for you guys? Excellent. And then in the y direction, I have normal equals mg. That good too? Well, we want the coefficient of static friction. I hope you remember that stuff. It seems to me if I want the coefficient of static friction, and if I want to do something that Mr. Shelton told me I should do, which is preserve the inequality, that I should substitute this in for the normal force and that in for the frictional force. So 0.033 has to be less than or equal to mu s times mass, which is 0.015, times g, which is 10. So mu s has to be greater than or equal to 0.033 divided by 0.015 divided by 10, and I get 0.22. Not terrible? Pretty straightforward, I think. Any questions here? All righty. So it tells me the minimum. The minimum is 0.22. It can be greater than that, but the minimum is 0.22. The actual coefficient of static friction is 0.4 between the little bug's feet and the record. What is the maximum distance away from the edge of the record where the bug can safely walk? Well, if I just work this problem backwards, we know kind of this side of it, right? So we know friction has got to be less than or equal to 0.4 times mg. That part hasn't changed. Right? But we also know that the net force is equal to friction in the x direction, which is equal to m omega squared times r. Right? We just did that. It's literally should still be on your paper from a few seconds ago. Do you see it there? So can I just do that? Since friction has to equal this m omega squared times r. Again, I like substituting into the inequality. Now, the first thing I want to point out is I could just cancel out those. That was m on both sides. I didn't actually need the mass of the bug to do this problem. Do you see how it cancels out? And omega stayed the same. Omega is still 4.7. There we go. We just got to figure out what r is. So 4 divided by 4.7 squared, I get 0.18. So that's 18 centimeters. The bug has to stay less than or equal to 18 centimeters away from the edge. If he tries to go 19, he gets flung off. So the bug better stay there if he wants to stay on. All good? Now, the last thing, you are expected to figure out what the linear velocity of the bug is. Linear velocity of the bug equals omega times r. So that's just 4.7 times 0.18. That's got to be the linear velocity of the bug. And I get 0.85 meters per second. Whee! Yay, bug. All right. So, dip and hill. not drawn great, but that's what I've got. I think I could do a little bit better job, but it's not gonna be much. There. This has a radius of 50 meters, and this has a radius of 50 meters. The car makes it to the bottom here, and it's traveling at 22 meters per second, and here, 22 meters per second. How many forces act on the car at the bottom of the dip? Two that matter. There's normal force and weight. Should the normal force be greater than, equal to, or less than the weight? We did this problem. We did it in class. It has to be greater than the weight. This is like the roller coaster car when it's at the bottom of the loop. It has to have an unbalanced force towards the center. So normal force has to be greater than the weight. This is a car traveling in a circle, so I'm not going to use omega. I'm going to use V. And here, the net force in the y direction has to be MAC, because it's traveling in a circle. I see two forces, normal and weight. So normal minus weight equals M V squared over R. So I want the normal force. So normal equals mg plus m v squared over r. We have all those things, right? They told us the mass of the car is 1,500. They told us v is 22 meters per second. They told us r is 50. So we can just plug all those in and get an answer? That good for you guys? So let's do the other one before we run out of time. On this car, there's going to be normal and weight. Is the normal going to be less than, equal to, or greater than the weight? I need an unbalanced force downwards, so the upward force must be less. Has to be. In fact, I want to make downwards positive. So mg minus normal equals m v squared over r. And now I have to solve that for normal force. So normal force equals mg minus m v squared over r. You got the numbers, just plug them in. All right.